Okay, so I just wanted to like do a quick little like screencast thing. Um, just for anybody who, cares enough to watch it. um, so, okay, first things first, I guess I will zoom in a lot. So, just the context for all of this is coming from we can think about the graph of the function f of x is x squared. So, like, we should understand what this graph does in general. And we can understand that better by making a little table of values. So when x is something, we have f of x. And let's just like, fill out a little basic table. When x is -5, when x is -4, when x is -3, when x is -2, when x is -1, when x is 0, when x is 1, 2, 3, 4, and 5. And like, if I'm plugging in -5 into x squared, that means my output has got to be 25. Because like f of -5 would be -5 squared equals 25. This one's got to be 16, right? This has got to be 9, this has got to be 4, this has got to be 1. 0 squared is 0, 1, 4, 9, 16, 25. Okay. So, like, all of that to say, this kind of generic quadratic function, it has a particular shape, right? Like it has yes, it's a parabola, but I mean like when x is 0, we definitely have that point. When x is 1, we've gone up to 1 on the output. When x is 2, we have 4. When x is 3, we have 5, 6, 7, 8, 9. When x is 5, or sorry, wait, so 1 is 1, 2 is 4, 3 is 9, 4 is 16. So 10, 11, 12, 13, 14, 15, 16. And I guess that's all I can do in terms of fitting it in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so I can't go up to 25. I don't have space, but I can also just show what's on the other side. It's the parabola. Any parabola has to be symmetrical. And I'm not even, I also have my table of values, so it's like, I'm not really like doing any guesswork or anything like that. As I go 1 away from the vertex, that's 1 squared. I've gone up 1. 2 away from the vertex, 2 squared. I've gone up 4. My output is 4. 3 away from the vertex, 3 squared. I go up to 9. So this pattern of like noticing it's jumping up 1, jumping up to 1, then jumping up to 4, then jumping up to 9, then jumping up to 16, then jumping up to 25. So that's going to come in handy when we are trying to figure out the A, or the vertical stretch or vertical compression factor of a quadratic. The quadratic function f in vertex form I'm basically trying to think, well, what transformations have been applied to the generic quadratic function f of x equals x squared. So see, like, if I had f of x equals x squared, I would be, like, I don't have space here, but I would be having that parabola that goes up like this, right? That we just dealt with. When I go over to 1, I go up 1. When I go over 2, I go up to 4. So how is this different? Well, first things first, it's been completely, like, inverted. So instead of having a parabola that's going up like this, like, it's completely inverted. So you definitely know A must be negative. That's just like a really, like, I don't even know why I'm making that observation though. It's just like, it's just true. A must be negative because the parabola is inverted. So, okay, finding H and finding K, that's no biggie, right? Like, finding H, finding K, completely fine. You know, literally, what's the vertex? The vertex is -4, -2. So that's not the weird part. And to be honest, if we look at this, well, when I go 1 unit away from the vertex, see how the pattern is the same as that graph of this function. The pattern is the same because I'm going, when I go away 1, the parabola is basically like, the change is 1 squared. 2 units away from the vertex, 2 squared is 4. So I actually already know A has to be -1, just because the value, like we definitely know A is still like either plus or -1. I guess A, we definitely know it's negative because it's inverted, but then see how it's like the same type of amount of vertical stretch or compression as this generic quadratic function. So here, this function definitely just has to be f of x equals -1 x plus 4 squared minus 2. It just literally has to be that. There's no other possibility. Let's say we're not comfortable making this visual, like, conclusion visually because we can see, oh, the pattern is the same. 1, 1, 2, 4. That's where you can alternatively, you can solve for a algebraically. How can we do that? Well, the way we can do that is, I don't really have much space, but it's fine. I'll just kind of try to make it work. The way we can do that is, we know for vertex form, we have to, this is what we're working with. Because we can just look at the vertex, we already know h and k. So let's make those changes. F of x equals a x squared. Let's do a different color to just show that we're changing. So it's got to be plus 4. Oh, did I do that wrong? Yeah, okay, good, I did that fine. Okay, so minus 2. So here's the thing. You might be thinking, oh, what do I go from here? But technically, if we have any points, if we have any points from the quadratic, the curve, we can plug them in as x and f of x. Because you can think about if there was a table of values. Imagine a table of values x and f of x. Like, we just have to have one point other than the vertex. So, well, we have other points. We know when x is -3, f of x is -3. We also, I could be good with that. I wouldn't have to do anything else, but let's just say I know another point too. I know that when x is -5, f of x is -3. And based on whichever points I know, I can just pick one. That's an x f of x pair. It's an input-output pair. I can replace that. So it can be -3, -3. So let me do that in a different color. -3, -3. Just trying to do something with my colors here. Plus 4 minus 2. I'm just trying to, again, be a little bit clever with my colors. So see, we literally just replaced things. We knew that the vertex had to be something, which we were able to plug in when we did that here. Then, because we can see any points at all, any point gives us an x and its associated output f of x. So we just pick any point and just plug that in. Now I have an equation with one unknown. So I'm back to like regular algebra. -3 equals a minus 2, because that's all going to become 1 squared. Okay, well, I'm almost there. Plus 2, a equals -1. So you can always solve for a if you know as long as you know the vertex and one other point. So, because yeah, by that point, I would have known a is -1. I could have plugged all that in. I would have gotten the same answer I got before. So let's just do one where it's not. See, I already know a is 1 here because 1, it jumps up 1. 2 jumps up 4 units. So I already know a is 1 here. Let's look for one for where a is not. Same thing, a is 1 here because it's jumping up. See, it's jumping up similar to the, like exactly the same as the graph of f of x equals x squared. So all that this is a horizontal translation 1 unit to the right. So let's think about this. Which translations have been applied to f of x equals x squared? Well, f of x equals x squared would be down here. That's your f of x equals x squared. So there's been no vertical stretch or compression. This hasn't been pulled up. It hasn't been pushed down, like in terms of stretching or compressing. It has just been moved, though. It just completely went 1 to the right. One unit to the right. Vertical translation 4 units up. So, oh yeah, and just to be more general, like just to be the most general, which transformations? Because transformations basically includes translations, but also these stretches and compressions. So, okay, but I'm still trying to find one that's not going to be like, okay, look at this. Okay, but that one's too, I want one that's like a little bit different. Wait, negative. Okay. I like this one. So, okay. We kind of have to read the graph a little bit. But so looking here, let's set up a little table of values. Why don't we just first say what the vertex is? When x is -3, the output is -3. Okay, so that's great because I definitely want my vertex to find vertex form, but one other point any other point. Any other point. Any other point. Any other point. Well, we have a lot to choose from, technically, but, well, I know that. So, -2, 0. Okay, I'm ready to go now. I'm ready to solve for whatever. So, if f of x equals a h, so for my vertex, it's going to be x plus 3 squared. Okay, I want to give myself space. F of x equals a x minus h, the horizontal translation, vertex hk. That's just the basics of vertex form, but plus 3 squared minus 3. Okay, so, how on earth am I going to find my a? Well, I actually have an input-output pair. When x is -2, the output is 0. Let's fill in everything else we had. So solving for a, 0 equals a minus 3. A equals 3. And that actually makes sense because when I go over 1 unit, I'm jumping up 3 units. When I go over 2 units, how many units have I jumped up? I've jumped up significantly. I've jumped up, that's like wild. Like when I've gone up over 2 units from the vertex, I've actually gone up 3. I mean, I guess it might be kind of like actually might actually be more like here. But here's the thing. If it's not clear enough to do it visually, you just do it algebraically, right? Like, but you can see if I go over 2, you are jumping up like to this f of x equals 9 space. So you're going up 12 because this 3 plus 9. So rather than the typical x squared, which would be jumping up 1 and then to 4, this is jumping up 3 and then to 12. So you know it's been stretched. It's been like pulled like this, like it's been pulled vertically, stretched vertically to make it basically go. I mean, I guess it's maybe better to just think about it being pulled up only. Kind of here's the vertex, we're pulling up from there. Okay, so all that to say is we'd have f of x equals -3 x plus 3 minus 3 squared. So that definitely has to be the case. And I wonder about, so let's see if we can do one more, just one that might be a fraction if that is in here. Oh, there's some over there. Oh, good. So, like, see, you can already kind of tell this one's been like, whoops. It's always a bit... My computer's a bit finicky when I use this app. Okay. Here we go. Okay. Vertex. Other points. Well, my vertex 2, 3, one other point 4, 4. Now I can solve. So f of x is a times x minus 2 squared plus 3. That's one thing, because I at least got to get my vertex in my vertex form, right? From the generic version of vertex form. So do that. And then, well, we know we want to solve for A. We want that to be our only unknown. So fortunately, we can plug stuff in here because it's an input-output pair. Any input, any output pair. Any input-output pair. So 4 equals A minus 2 squared plus 3. 4 equals A times 4 plus 3 minus 3. Oh, here, let me just make this look a little nicer. This is a regular two-step equation. Divide both sides by 4. A has to be 1 over 4. And it actually kind of makes sense because the pattern here is instead of, again, if it was the, let me use a different color. If we were, or let's just say in comparison, to f of x equals x squared, which would be down here, jumping up 1 over 2, jumping up to 4 over 3, jumping up to 9, which I can't draw, but like that's significantly like more like kind of, here, one sec. Like you can tell it's been like flattened. It looks, I'm like motioning with my hands right now, but it's been like squashed like this way. There's been like a squash down on it. And now I actually have to go over 2 units from the vertex to jump up 1. Whereas before, with this quadratic, if I would have gone over 2, I would have jumped up to 4. So see, it's the difference between jumping up 4 units versus 1 unit. So you know that's like it's literally 1/4. It's only jumping up 1/4 of the amount because it's been that vertical compression downwards. So this blue, we'd have the A, which we calculated was x plus 2, minus 2 squared. Did I mess that up over there? No, we're good, plus 3. So, I don't know, I just wanted to help because I just feel like it's just, it's really fun once you understand that part, I feel, because, yeah, I don't know, I just think it's cool. 2, 3, yeah, like, I think these are all fine in terms of answers being correct. So, and you can start to see, like, yes, you could solve algebraically for like this one, and no one's going to stop you, but you can also already see how, like, we have a vertex here. When I go 1 unit over from the vertex in either direction, I'm jumping up 2 instead of 1. So I know that's already got an a of 2. Oh, a of negative 2, because I know it's negative because it's been inverted. It's been reflected across the x-axis. Relative to the generic quadratic function f of x equals x squared. Okay, that's that, I think.